start with a lighter note. Have you done the problems? Anybody? You showed me the first one. That seems more or less correct to me. I haven't checked the numbers, but let's see. I mean, there were two problems that we discussed, right? One was for this anharmonic oscillator, trying to calculate something with ladder operators. I know one person has tried, and that looks correct to me. That's good. But has anybody else tried and succeeded in doing that problem? Let's say, I mean, okay, whoever has succeeded or at least tried, please raise your hands. Okay, you have tried, okay, but have you succeeded? Oh, where did you get stuck? Oh, I see. But, okay, let's see. So, who else tried? Somebody, oh, you also tried, but did you succeed?
No, sir.
So,
I did not know how to this X and A and A dagger acts on N.
no, but I gave that there, right? So, but you could have also derived it yourself. So, sorry, A dagger acting on N. I think I wrote that on the board the last time. And I think I wrote these things down when I gave you the problem. Also, I derived it in the class as well. So, yeah. So, now can you do this? So, I have given you the action. So, right. But let's see. So, did people realize one central thing? So, of course, there is this n, and then inside you have x to the power 4, and you can break it into some a plus a dagger whole to the power 4, and then you get many terms. Without doing any calculation, can you figure out which of the terms do not contribute to the answer? There are some terms which would never contribute. I know you have done it, so good. But did you manage to see that? Okay, good. So, no, not, okay, sorry. So, it's, let's say I'm missing some coefficients and all, but let's say some structure like this, right? So, what does it mean? That there are like, it's a product of this same thing 4 times, right? So, let me give you one particular term out of this product, okay? This term, A dagger. What is this object? What do you think this object is? This one, just by our rules that we have discussed. So, remember what A dagger does? A dagger raises the n to the higher eigenstate, and A sort of pulls it down. So, you see what we have to do, right? I mean, this is n and this is the same n. So, what do you think? Correct. So, if this acts, then I will go to n plus 1, then I come here, I again go to n, then I go to n minus 1, then I go to n minus 2. But of course, n minus 2 is orthogonal to n, so that's 0, right? Good. So, the only kinds of terms which would contribute to this are which have the same number of A daggers and A's, right? So, that's the first simplification, right? So, please use that and please use these, and then you will be able to solve the problem. But please try it, right? Because then you will see that everything comes out very nicely. Okay. But now can you solve this problem? After I tell you this, I mean, you see, this is one thing that you require, and that is the other simple thing that you require, right? So, please solve it, and yeah, okay, good. Okay, and yeah, I guess, okay, try to solve it in real time. I don't know. Depends on which step you are. Are you close to the answer? Or okay, just solve it in your sweet time. Don't worry. Okay, good. This was one problem, right? There was another problem given. Did anybody try that? You tried it? And then what happened? So, oh, I see. Okay, so let's see. Let's again write down the problem just to remind everybody. So, it was a problem which is just a simple generalization of the single spin problem that we did. So, now we have 2 spin halves, right? And the Hamiltonian was this. This was the Hamiltonian, right? And you were asked to find the partition function and other things, magnetization and so on at finite temperature, right? This was the problem. So let's see. Who are the people who have attempted it? Okay. Okay. So somehow people got very scared with 2 spins, I see. Why? I mean, what is a doublet? I don't know. What is a doublet? Triplet. Will be the? Okay, correct. So there is one hint for you. So, and what are the Eigen Energies? Let's see if I calculated it in my notebook when at the end of PK's lecture. So I listened to your lecture and then calculated. Okay, so no, there's no J, right? I put 1 here. Just you can come to the board and explain. Oh, you don't want to? Why? Okay, fine. I mean, oh, because it's recorded. Ah, that's fine. Don't come to the board. Yeah, don't come to the board. Right. Okay, good. Yeah, you're correct. I mean, there are 4 eigenstates, but how do you find the eigenvalues? I mean, you try to write this thing in some other form, right? S1 dot S2. No, there is something even simpler you can do. For example, what is special about the 3 triplet states and the 1 singlet state? What is special about them? Yeah, correct. They are eigenstates of S total, right? They are eigenstates of this operator. They are eigenstates of this guy, right? So and of course you know that the singlet carries S total equal to 0 and the 3 triplets carry S total equal to 1, right? Good. So of course you can calculate the action of this operator on this, and this would be the eigenvalue, right? So then can somebody say how to simplify this object? Correct. And then? Good. And that's it? Very good. Divided by 2. Now everybody should be able to calculate this thing, right? So let's see. What is the singlet state? So let's put some notation. What is the singlet state? Okay. Is that it? So I have to normalize it. So right. Then there are 3 triplet states, right? So this is already normalized. This is also normalized. So can the rest of the class follow this? I mean, it's important to see that, okay, you can try to check for yourself. If you haven't seen this, please check for yourself that these 4 eigenstates are the eigenstates of S total operator. Okay, that's the first thing to check, and then the rest would follow. Okay, and this guy has S total equal to 0, and this has equal to 1. Okay, please check that. Okay, good. So then I'll just say 1 or 2 things and then please try to solve the problem after that. Now you see it should be evident to you what to do. So you go to the energy basis and then let's say I draw the energy as a function of H. Okay. So there are 4 states, right? So there are 4 states. So let's say this is 0 energy. So let's see. Let's say at 0 energy I tell you that the energy of this guy is minus 3 by 4. You can check that. And the energy of these 3 guys is plus 1 by 4. Let's say I tell you that. Then could you please tell me how I should draw the 4 energies at finite H? So I've given you the 4 states and I tell you that at H equal to 0, the energy of this state is minus 3/4 and the energy of these 3 states is plus 1/4. So now how should I draw the curves at finite H? I mean, how is the energy evolving for all the 4 states? So let's start with the singlet. Let's start one by one. So let's look at this guy. Singlet. What is going to happen? What is that constant? Good. So this is 0. So let's say I have to draw this. Let's say this is also 0. So, okay, or whatever. This is minus 3 by 4, let's say. So this number is minus 3 by 4, and this is the energy of the singlet. This thing does not change with magnetic field because the total Sz is 0, right? So it doesn't change with magnetic field. Okay, now which other state should I look at? Maybe this one, right? This again stays constant, right? So plus 1 by 4. What about the other two states? Let's first look at this guy. Yeah, but what is the slope? I mean, what should I do? Minus 1 by 4 plus, plus 1 by 4 plus what or minus what? Actually h, right, because it's spin half. So for up it will be plus 1 by 4 minus h, correct? Because, yeah? No, actually, oh yeah, because there is a minus sign. Yes, that's correct. So it will keep going down, right? And it will cross this guy somewhere. Do you agree? Okay. So it's plus 1 by 4 minus h. And this guy is plus 1 by 4 plus h, right? So let's mark this. This is which state? This is the state T1, yeah? This is the state T2. This is the state T3. This is the state S. Now I hope everybody should be able to calculate the partition function and everything else. I hope, right? So then please do the calculations, and then let me ask you one or two simple questions for which you don't even need to calculate the partition function. So let's say I'm here at this magnetic field, and let's say I calculate the specific heat at low temperature. What do you think the form of the specific heat would be? What? Exponential and some gap in T, right? Now is this thing true everywhere for all magnetic fields? Where should it fail? Right, correct. Then suppose you calculate things like susceptibility of this system, right? Then again something interesting should happen here, right? And then similarly if you calculate this problem at finite temperature, there will be various things you would realize then. So you see, I have given you all the information here, right? Now you should be able to solve everything. I mean, you don't need more information to solve this problem, right? So just try to solve it, and then maybe tomorrow afternoon when everybody is again tired, we'll discuss it again, right? See, but this is not hard, right? I mean, so just try it. Good? Everybody is clear on what I did, right? So now you can solve it. Good. No, now don't go to sleep. Okay, so good. So let me then perhaps, okay, of course, first, I mean, do you have any other questions for me which I can try to address? What? Where? Here? No, there will be no phase transition. No. Yeah, I mean, okay, there is some levels which are crossing, that is absolutely correct. So, but you won't call it a phase transition. Why? No, what do you mean okay? I just repeated why and you said okay. Yeah, that's one way of saying it. There's no spontaneous symmetry breaking, etc., etc. But if you calculate the things, for example, if you calculate specific heat, for example, here, you would see that even when you pass through this point, there won't be anything singular here. Okay, that's part of the answer, if you wish. Of course, there will be some interesting thing when you approach this point, but it won't be singular. So you have to do that calculation, right? You cannot mentally do it. You have to like write everything down on a piece of paper, and then you have all the information, you can just calculate.
No, but for the phase transition, right, this partition function was lambda max to the power L. So the largest tangible when something else cross, then the lambda max actually become non-analytic at some point. Here, there is nothing like that, right? This is not the that Eigen value or something. There is two
No, the short answer is you calculate the specific heat, just calculate, okay. Sometimes in life just calculate, okay. Just calculate the specific heat and see what is the behavior, right. Not everything can be seen in thought, just calculate. No, sometimes people should calculate, right. So, just calculate, this is easy, right. I mean, no, what do you want to say?
No, I'm saying that if these are the eigenvalue spectrum of a transfer matrix even, this will not be called a phase transition.
No, but these are of course not eigenvalues of a transfer matrix.
No, but I mean the guy is confused about the eigenvalue crossing and phase transition. That's what he is asking.
Okay. But just calculate. No, but okay. I mean, just coming to your question, just because two energy levels are crossing each other, that does not necessarily imply that there is a phase transition. That's the short answer. I mean, there are many situations where energy levels cross each other, but it doesn't mean that there is a phase transition. You look very unhappy. Would you calculate this thing, right? I mean, this is straightforward. Just do it, right? Then you will see what I mean, right? Okay. What else? Does somebody have any question?
So you had mentioned a little about the superfluids.
I had also mentioned that it's beyond the scope of these lectures. But what is your question? What is your question? Yeah, but it's very okay. I mean, it'll just make you more confused. It's first good to understand these basic things. I mean, there is no point in trying to jump the gun. So just if you want to read a bit about superfluids, I can tell you a good place to start is one of the books given to you as part of this refresher course, which is Carson Huang. There is a small section in Carson Huang which is about 10 pages or something, if I remember correctly from my graduate school. So please try to read that. Please try to read that. It's not very easy, but please make an attempt to read it, and at least you'll get some information, right? And when you read it the first time, I'm sure you won't understand it completely, but at least it's given in a nice logical fashion, right? So Carson Huang, and that's already a book given to you, right? So. I mean, one reason I don't want to start with that is that requires quite a bit of background work. So, it's better to just read it therefore from that textbook. Yeah. What else? Okay, so then tomorrow afternoon we'll again come back to this problem. Okay, and hopefully some of you would have solved the problem, right? So, the things to do is you should find the average magnetization. Sorry, this is bad notation. What did I use? S1. So you should find this, and this is of course going to be equal to that, but you can just easily verify that, right? You can also find the specific heat, right, as a function of temperature and magnetic field, because these are the only parameters here. There is no other parameter here, and also you can try to find the susceptibility. Okay, so for susceptibility you just need to find the total magnetization, which you already know from this calculation as a function of H and T, and the derivative of that with the magnetic field will give you the susceptibility, right? So please try to find these three things. Okay, susceptibility, specific heat, and this. Okay, good. Okay, so if there are no further questions, let me just continue my discussion of the phase transitions. Let me just wait for 5 minutes in case somebody thinks of something to ask. Not 5 minutes, 2 or 3 minutes, and then of course if there's anything unclear about any of the previous lectures also you can ask and I can try to answer. Please, go ahead.
We were discussing that phenomenon example.
Yes, yes.
We took the minimum energy to be zero.
In that particular problem.
While we were taking finding fugacity.
Correct, correct, correct. Why did we do that?
It's not zero, then our range for fugacity will change.
Yes, exactly. It will change.
So in that case, we'll have to do a completely different calculation.
That is true, but that is of course true. But the case we were dealing with was a gas of free bosons where it was naturally the minimum energy was 0. Now your question is that what happens if I take a totally general problem? Okay, in principle the thing can form some bound states and then the energy can go below 0 in principle. But yeah, in practice, if you just takes this system of bosons and just put weak interactions between them, that does not happen. So that still goes through that range of fugacity, right? Yeah, but yeah, in general it can change. Yes, yes, yes. What was the other limit? The 1 is a bit difficult to change because that is the high temperature limit, and in the high temperature limit you should recover the classical result, so it should go to 1. Yeah, yeah. Okay, if there are no further questions, let's continue our discussion of the phase transitions which we were at. And yeah. Okay, so one thing I forgot to mention, which I should mention now, is the following. So, of course, I think there was also a question in one of the previous lectures. There's this Ehrenfest classification of phase transitions, right? But when we think of these order parameters, as we had just discussed in the previous lecture, there's a more natural way of defining what kind of phase transition it is, and that's also very easy to remember. So we just talk of sort of two different kinds of phase transitions. One is a discontinuous phase transition and one is a continuous phase transition, and that's it. And the definition is sort of clear. So there's an order parameter and there is some temperature which you're tuning, or in general it can be some other tuning parameter also. So see, as I said, there is some state where the symmetry is not broken. So then the order parameter is 0 by definition. Let's say above Tc, right? So it's 0 by definition here. Whereas below Tc, it becomes a non-zero value. Now the question is, as you approach Tc, how does it go to 0? That's the question. So it can only go to 0 in two manners, right? Either it can go to 0 continuously, right, and then stay 0. So this is one possibility. Or the second possibility is that it can do this, and then there is a discontinuous jump, and then it becomes 0, right? So both the possibilities exist. So this we call a discontinuous phase transition, and this is also called the first order phase transition. But in this way of looking at it, you can just say that this is a discontinuous phase transition, and this is a continuous phase transition. So you see, in this way of looking at things, there are only two possibilities: discontinuous phase transition, continuous phase transition, and that's it. We will see then that continuous phase transitions has some other very interesting properties, and that Ising model example that we were doing in 2D is an example of a continuous phase transition. But of course, we also know of first order phase transitions, several examples. So yeah, so both examples exist. But this is now very easy to remember, right? So you look at the order parameter behavior near Tc. If there is a discontinuous jump, you call it a discontinuous phase transition. If the decrease in the order parameter is continuous and it smoothly goes to 0 like that without any jump, then it's a continuous phase transition. Okay, good. So this is one sort of classification I just wanted to point out. So now let's again go back to the one-dimensional short-range Ising model. So of course we learnt in the previous lectures that there is no phase transition there if the model is short range because of the Perron-Frobenius theorem, right? But let's try to think of it in a slightly different way, and then we'll go to 2D and we'll also go to this mean field theory, right? Okay. So let's try to think of it slightly differently. Okay, so of course, let's say I'm at t equal to 0, right, for the one-dimensionalizing model. Let's say I define a ferromagnetic one-dimensionalizing model, right? So let's say I'm at t equal to 0. So this is my ground state, one of the ground states. So let's say I start with this one, right, at t equal to 0. Now, when I'm at finite temperature, not only I should not really minimize energy, I should really be minimizing free energy, right? That's the key point. So at any finite temperature, I should be minimizing free energy. So then you ask, let's try to estimate what is the free energy created by, let's say, 1 spin flip, 2 spin flips, so on and so forth, right? We can easily ask that question. Good. So now, coming to this state, the free energy of this state is just, let's say there are n bonds minus n times j, right? Because there is no entropy to this state. Now I choose a bunch of spin. Suppose I choose one spin, this guy, and I just flip it. So maybe I use a, no, this is not a good color. So let's say I just choose one particular spin and I flip it. Let's say this spin, I just flip it. So there is some energy cost which I create, right? Because I break these two bonds. So basically the delta E that I pay is something like 4j, right? Or is it 2j? Okay, 4j, right? So that's the delta E that I sort of pay, right? Good. But what is the entropy of such configurations which live at this energy, for example? What do you think is the entropy? Sorry? Entropy. So just, yeah, okay. So just let's just count this guy. Log of the number of possibilities, right, at that energy. Exactly, right. So because I can just place them in any of the n sides, this spin flip. But you see there is something else. There is no need to just flip one spin. I can in fact flip an entire block of spins here, right, like this. And I would pay still the same energy cost because the energy cost just comes from these two ends, right? I mean, it doesn't matter if you flip one spin or an entire patch of spins together. I mean, it's exactly the same energy cost, right? So there are in fact many such events which can happen, and for all of them, the delta F compared to this guy would be 4j. So there's an excess energy, but as we just said, there's an entropy gain, log n, right? Agreed, right? So if I think of these configurations where maybe there are these domains, and in fact I have underestimated the entropy because of course, as I said, this patch can be of various sizes as well, then you can say that at least I'll gain this much, right? Now if I'm at finite temperature, and let's say my n is large, then do I do better for free energy or worse? Is the free energy getting increased with respect to the state, or is it decreasing? It's decreasing, right? So this kind of a state is clearly better than this domain free state, right? Good. Now let's do something else. Let's just do a higher version of this. So let's say that I have the same background state, and I choose a patch of spins, again of some length here, and maybe a patch of spins of some other different length here, right? Good. And then I just turn them down, this patch of spins, and turn all the spins in this patch down as well. So let's say the patches are reasonably well separated in this large system, right? Then what is the free energy change here? So first, what is the energy cost? 8j, right? Because you don't care about the length inside here and the length inside here. That can also fluctuate a bit, but it's just 8j, right? And Okay, what is happening here? How many possibilities are there? Suppose n is very large and I say that these patches are reasonably far apart. They don't really touch. So how many possibilities? Correct. So it's n square, right? The number of possibilities are n square. So that's basically 2 times t times log of n, right? So it's exactly twice of this. So there's an even bigger free energy gain, right? Clear? Right? And so on and so forth. Now, of course, you can see what's going to happen. Suppose I have this string of up spins, right? And I just freely create small n number of patches anywhere, somewhere, like, so small n number of patches. The free energy gain due to that would be small n times 4j minus t log n, right? So at any finite temperature, therefore, it's clear that basically these domains will just proliferate throughout the system. They'll just freely move around throughout the system, right? And that is what actually destroys the order at any finite temperature, right? Because these things just kill the order, right? Because these patches I could have selected to be small, large, and then I can select n of them. In fact, they give a bigger free energy gain, and so on and so forth. So this argument actually tells you, at least in some way, I think reasonably, that you cannot have long range order at finite temperature, right? I don't know, is there a way to state it slightly better than this? I think, yeah.
You have a state with the uniform magnetization, you can always
Exactly.
create something with lower magnetization with larger entropy.
Exactly, and the entropy gain just increases as you have more and more patches. Yeah, so that state cannot be stable, right?
Maybe you can point out what goes wrong in this argument in 2 dimensions.
That's what I'm going to do right now. Yeah. Okay. So in 1D, I hope everybody is convinced that we get a lot of free energy gain by just proliferating the domains all around the system. And because we are doing that, the long range order cannot survive at finite temperature.
And for all sorts of interactions.
Short range. Yeah.
That short range is
Ah, see, good. See, the short rangeness comes from the fact that I'm just counting the boundaries here, right? I mean, it's not so simple if you have long range interactions. You cannot make these arguments so simply, and then some more subtle thing can happen, right? So, in fact, it does happen in some cases, right? Oh, so, okay, that's a bit technical. My definition of short range is that, let's say the interaction between the spins is decreasing exponentially at some large length scale. That's a reasonable definition. Yeah, you can also generalize this to power laws, but that's a bit more difficult. But exponential is fine. Yeah. Oh, I see. See, okay, see, what's exactly happening here? Suppose you look at this picture, right? Just look at this picture. This patch of spins and this patch of spins could have been here, could have been here, could have been here. They have exactly the same energy, right? And that's what gives them an entropy gain, right? And that entropy gain really compensates a lot more than the energy cost, right? Because the entropy gain is increasing as log of n, right? And then, because these patches can just be anywhere, they'll just try to maximize the, minimize the free energy by maximizing the entropy. And then these domain walls will just freely move around in your entire system. And note, you can just have not only one domain wall, 2 domain walls, you can have 3, 4, 5 and so on, because the more the number of domain walls, the bigger is your free energy gain, right? So then you can imagine that if you just have these domain walls where the spins are pointing in the other way, freely moving in your system, then the long range order cannot survive, right? That's roughly the argument. And of course, we saw an analytic proof of this as well. Okay, now let's come to 2D. Okay, so what changes in this argument in 2 dimensions? Okay. So let's again start with a 0 temperature phase in 2D where all the spins are let's say plus, right, or up in direction. So let me just draw plus because it'll help me draw things better. So let's just draw some plus spins and then I'll change something. So the key thing which happened in 1D is this domain size. See, this domain can be big, small, so on and so forth, but the energy cost of the domain is just caused by the endpoints of the domain. That's it, right? So that's it. You just count how many endpoints are there and that gives you the energy cost. In 2D, we'll see that the situation is different. Okay, now let's just flip some spins. Let me draw one more row. And let's flip some spins now. Let me draw a boundary. Oh, sorry. Let me not flip this. And so let me draw this picture slightly better and so okay, let me draw it with a different color. So I'm making a domain in 2D. Okay, that's what I'm doing, and I'll flip all the spins inside the domain. So I'm doing exactly the same thing as I did in 1D. That's what I'm trying to do. And I'll flip all the spins inside. So all these spins become minus, okay? So let's just do that. Okay, so you can see what is the domain here, right? Everybody can see what's the domain here. Now, how does the energy of the domain scale here is the question. How does the energy scale here? So I need to give you some information. Let's say I tell you what is sort of the perimeter of this domain, right? So let's say I just tell you that, and then you have to tell me how does it scale. So let's say I denote the sort of perimeter of the domain by some small l, right? So the perimeter of the domain is roughly telling you, see, where is the energy cost? It's in the boundaries of the domain, not in the interiors, right? So the energy cost is in these bonds. So the wavy lines that I'm drawing, right? Like this, like this, like that, like that. I hope I haven't missed anything. I think not. Like that. Right? So these bonds on the boundaries are the one which give you the extra energy cost, right? So clearly the energy cost is now proportional to the perimeter of this region. Here the energy cost was just proportional to the endpoints, but here the energy cost is proportional to the perimeter, right? So let's say the perimeter is small l. So then sort of if I again want to estimate the free energy cost of this over the ground state, what do you think is the energy term? Yeah, something like that. 4, yeah, whatever. I can put 2 or 4, doesn't matter. So let's put 2 JL. Yeah, doesn't matter. Yeah, something like that. Okay. Now comes the next question. so of course now I have to estimate the number of ways of trying to create this kind of a domain wall, right? Trying to create this kind of a structure, and the only thing I should remember is that this structure should have basically the same perimeter. Whatever I draw, whatever shape I draw, maybe I can draw some other shape here, some more complicated shape here, but that shape should also have the same L, small l. If it has the same small l, then of course the energy cost is still the same, and therefore in my entropy sum I should also include that state, right? So now the question is, in how many ways can I do this? Here of course you could just move in 1D. So it was a simple exercise to see that it's proportional to the number of spins, because I can just move one way, but here I can move in more than one ways, right? So what do you think, how many possibilities are there? So effectively what is the problem? It's like I give you some sticks if you wish, and the sticks could be sort of horizontal or vertical. In fact, one way of imagining it is you are on the square lattice, and then in principle you can go like this on any of the bonds of the square lattice, right? Like that. Maybe in the next instance you go there, next instant you go there, and you don't want to cross back because yeah, I mean, why would you cross back? Because you just want to form a path like this, right? There's no meaning to crossing back here. So then the question is, the only restriction given to you is that the structure that you draw, it should just close onto itself, and the number of steps that you take is, let's say, small l. These are the only two constraints you have, right? And let's say small l is some reasonably large number. Let's say I want to take 20 steps or 40 steps, right? So this is the only restriction given to me. Then roughly what do you think, how does the number of ways of drawing such paths scale with small l? That's the question, right? Proportional to area of what? No, but the loops can be of a variety of shapes and sizes, right? For example, this is one loop, but I can draw a really elongated one, right? With L by 2 here, maybe 1 here, something like this also. So then spins inside. But the spins inside don't matter to me. What matters to me is the perimeter. Because see, this guy has far less spins inside, but I'm paying the same energy cost, right? So the question is, yeah. How would you sort of do this? Roughly one way of doing it is, maybe there is a cleverer way of proving this, but one way of thinking about this is the following. This is essentially like a random walk in some sense, right? So it's like this. Let's say I go here. Of course, I go here with some probability. There were 4 ways. I could have chosen any one of them. Then I said I don't want to cross back. So then I can choose any of these 3 paths again, right? So I choose that. Then I can choose any of these remaining 3 paths and so on, right? And then I can keep drawing a path like this by random choices. The only thing is I need to close back. That's the only thing. I need to close back, and that's it. And then if I have these L steps, I'll close back and my perimeter would be correct. And then to calculate the exact number is hard. It's sort of obvious that the number of these possibilities therefore increases exponentially in small l. Right? Because, okay, by this naive argument, I would have said 3 to the power L, because in some sense I'm saying 3 possibilities at every point. But of course, as I keep drawing this path, like in the next path, there might be some guy where both this and this are covered, so there are only 2 possibilities, right? So that is a slightly complicated problem of how to estimate this number C. But at least I think this is clear that the number of paths grows exponentially in small l. The number of possible paths that you can draw, right? I mean, I don't know. I mean, is there any better way of explaining this?
No, the standard argument is the one given by Pius. What he does is estimate it to be 3 to the L, saying that, you know, let the entropy be as large as that. We don't mind.
Oh, okay.
That there is a rigorous bound on TC. I mean,
right.
Given some temperature, you can easily prove, even if it's 3.
Correct. this thing would order, right? So let's take it to be 3 to the L, right? But probably this number is not exactly 3, but yeah, yeah, exactly. Yeah, because it has to be smaller.
But we give entropy a little
Yeah. That's correct. So this is like worsening my possibilities of having a. So if I can show a phase transition here, there must be a phase transition, right? Okay, right, good. So then what do I do here? Now it's really nice. Now I take the log of this thing, and then you see there is a very nice balancing act which comes here, right? Because I get something like this, and then you can take L outside, and then you essentially get this, right? This is the free energy gain for such a thing. Now, okay, suppose your temperature is, okay, now you see, whether I would call it a free energy gain or a free energy loss really depends on the sign of this term, right? Because suppose my temperature is big enough, right? Of course, in this argument, the magical temperature is just given by this relation. Okay. Suppose my temperature is bigger than this magical temperature, right? Then of course you can see that creating domains is again very favorable, and you would therefore create lots of them, right? In fact, again exactly like that case, if you have a longer perimeter, a bigger perimeter, then that free energy gain is even more, because there is this prefactor L, right? So then if you are above this temperature, you will freely again create domains and you will destabilize the order completely, right? Good. However, let's say you are well below this temperature T star, then what happens? Then you can see that this domain is in fact costing you free energy, right? So of course it would occur, but it would occur with some probability, and the probability is given by this, right? And then if you want to draw a bigger domain, it will occur with an even smaller probability, because there is this prefactor small l sitting here. You want to draw an even bigger domain, then there is an even smaller probability of that. So if you then go through this argument, what you will realize is if you are at a temperature below T star, of course the magnetization won't be precisely 1, which it is at 0 temperature, because there are some of these domains which have reasonable probability, but then to get really big domains is a very small probability event, and therefore this order would actually survive. And that's essentially the argument, right? So the key difference between 1D and 2D is here the energy actually is proportional to the perimeter, and the entropy gain is much more because this is a two-dimensional system. Whereas there, the energy cost is just proportional to these 2 points, the boundaries, and the entropy gain is just linear in the system size or n square or so on. But if you take the logarithm of that, you just get log n. Of course, here in 1D, that's enough to destroy the order. But in 2D, there is this very interesting competition which arises, right? So that's essentially the argument. Good. Any questions on this? So basically, the key point is trying to see the competition between energy and entropy and try to see which one wins in 1D versus 2D. That's the difference. In 1D, we see that entropy immediately wins, whereas in 2D, we see that we need to cross a threshold before this happens. Okay. Any questions? Okay, if not, then I go on. Now let me do an approximate calculation. So see, this is of course, I mean, I haven't proven to you that, well, at least I have proven to you that there must be a phase transition in 2D, but I haven't told you how to calculate the critical temperature and so on and so forth. So now, okay, let me first do this thing about the Ising model, then I'll come to the mean field. Let me actually now tell you one trick through which I can even calculate this TC exactly. So let me first do that and then I'll come to mean field theory. So as I said, Onsager actually already proved that in the 2D Ising model there is a phase transition, because he basically solved the partition function, and therefore not only could he show that there is a phase transition, he could show much more. Okay, But even before Onsager, so Onsager's solution was in 1944 or 45, I think, 44, okay, 1944. But even before that, I think I have the reference. Yeah, in 1941 actually, there was a very nice solution, and I'll actually write the solution to estimate the TC. So basically, it was realized that in this Ising model, suppose I start from the low temperature state, right? Let's say I'm at very low temperature, right? Then somebody can ask, then how do I approach this problem systematically? One way of approaching the problem systematically is I start from low temperature and try to set up a low temperature expansion. I use the fact that the temperature is low. So then I try to write the partition function in terms of a series expansion, okay? Another complementary approach is you start from very high temperature and again try to develop an expansion of the partition function in terms of a series expansion using the fact that the temperature is high. So one thing is the low temperature expansion of the partition function, the other thing is the high temperature expansion of the partition function. So I'm going to do both here, and then we'll see that there is a very interesting connection between the low temperature expansion of the 2D Ising model and the high temperature expansion of the 2D Ising model, which allows us to find TC. Okay, so that's the idea, and therefore we'll get TC. Okay.
This 41 paper is the one of Thomas and Wadia?
Yeah, yeah, yeah. Oh yeah. When I would have got the duality, I would have mentioned their names. Oh. Yes, yes. That's yeah. Right. So okay, good. So basically, for this thing, I'm following a particular reviews of modern physics. I'll write that reference. And it's a really beautiful paper to read for anybody interested in these things. And suppose in your college or university you find some extremely good student who may be interested in doing statistical mechanics or physics in general. Maybe you can give him or her to read this paper as well. This is a very beautiful paper. Because even if somebody is a third-year undergrad or maybe slightly advanced, there are some things which that person would understand from this paper. So the paper is Reviews of Modern Physics by Kogut, and I'll write the title just to emphasize on you that when you're doing statistical physics, actually not only are you doing statistical physics, you're sometimes without realizing doing things which are relevant to even high energy physics and other fields. So the title of this article is An Introduction to Lattice Gauge Theory and Spin Systems. And this is Reviews of Modern Physics. Volume 51. And this is the page number. And with this information, you can find this article. Okay, it's a really nice article, and it gives you very interesting connections between one-dimensional, two-dimensional, three-dimensional spin systems, many of the spin systems we have studied here, and gauge theories. So they are not very apparent immediately, but there is a very deep connection between spin systems and gauge theories. So it's yeah, very interesting article. Oh, so one of the gauge theories which you're already familiar with is electromagnetic theory. Yeah, so that's one of the gauge theories. So yeah, without going into too much detail, one way of thinking about the gauge theory is the following. Okay, so you know that in electromagnetism you can write down the Maxwell's laws, right? So you write down the 4 Maxwell's laws. And then from that you can formulate something where you use a potential, a V, and an A, a vector field. And then you immediately realize that there is some redundancy in your formula, in your formulation. You can do some gauge transformations and still your equations remain the same. This you must have encountered in your electromagnetism, right? So, if you want to think about it, right now we were discussing models which have global symmetries, right? So, this Ising model had a spin inversion symmetry, that was a global symmetry, whereas these gauge theories have what is called local symmetries. So, yeah. Okay, so that just means that locally I can do something and some equations of motion stay the same. So then you would think, why on earth would people think of such crazy things as local symmetries and so on? It turns out that when we do field theory, if we want to describe certain forces and certain laws of nature, this is the only way to describe them. Gauge theory is the only local way of writing down these theories. That's why these theories naturally come to us, right? But then still you might not be satisfied. You say that, oh, how can I want a theory which has this local sort of invariance? Well, as I said, Maxwell's theory, Maxwell's electrodynamics is one of the examples. There are many other examples. But the point is, there is a way to think about these theories with local symmetry and map them into these spin systems which somehow are free of this, and you can actually solve one thing for the spin model and actually get something else for the gauge theory. So in gauge theories, particularly if you talk to people who do quantum chromodynamics, there is something called confinement to deconfinement transition. Maybe some of you have heard of this term, confinement to deconfinement transition. In certain limits, you can actually show that's exactly in the same universality class of the phase transitions of certain spin models. So that's a remarkable statement, right? And that actually helps you understand the physics of this confinement deconfinement transition, which happens in some quantum chromodynamics. And this is also the theory which is applicable for this plasma which is formed in these big linear colliders, right? So it actually tells you about some physics happening for those kinds of systems just by studying these kinds of systems. So I think that's remarkable. So, right. Of course, for more, please refer to this article. So, yes, I wouldn't say much more than that. Okay, good. Yes. Yeah, for example, yes. So, then, okay, so basically the point is that, yeah, I don't want to go to too much detail. So, when you write something's called quantum field theories, then suppose you demand that whatever quote unquote Hamiltonian, of course it's not a Hamiltonian that you write, is local. Then if you want to describe certain spin particles like spin 1, spin 2 or spin 3/2, you have to have a gauge theory. I mean, people don't know of any other formulation which gives you these kinds of excitations. But anyway, I mean, look, there is this whole paper which is written by a person who's much smarter than me. So just go and read this paper. That's it, right? So, I mean, that's why I give you these references, right? It's much better to read these references, right? Okay, good. Okay, back to Ising model. Now I'll do a low temperature expansion of the Ising model and a high temperature expansion. But let me first make a small comment. So before we even do embark on these expansions, actually doing these expansions in general is very nice. The reason is the following. Suppose you have some unknown model and you don't have the luxury of an exact solution, right? Then of course you initially start with simpler things to do, things which you can do in general, right? One thing which you can do in general for any model is a low temperature expansion of the partition function and a high temperature expansion of the partition function. That you can do. There is a machinery, you can do that. It may take you some time, but there's a well-defined way to do that. Good. Then, let's say you get the first few terms of a series and then you try to do some clever convergence tests and you can somehow prove that the radius of convergence of, let's say, your high temperature expansion is finite. That immediately means, and then you also prove somehow this for your low temperature expansion. That immediately means that whatever state you're starting with at high temperature, that is stable up till a certain temperature at least, right? Because the radius of convergence is finite. And similarly, if you start from the reverse direction and you show it for the other problem, you also know that the radius of convergence is finite for the other problem, and therefore it's one very practical way of knowing whether a problem has or does not have a phase transition. So I'll do something for the 2D Ising model now. I'll do the low temperature expansion, but I encourage you to do the same exercise for the 1D Ising model. Please do the low temperature expansion for the 1D Ising model. It'll be easier than the 2D Ising model. And then please try to estimate the radius of convergence. You will find that the radius of convergence is 0. It's a very sharp statement, right? And then of course you will know that there is no phase transition at finite temperature. End of story, right? So, and this you could have done with not just the Ising model, but some other more complicated model with more interactions given, right? That's why I'm saying that it's a very useful thing to know and teach, because there are very few models in physics where you can do an exact solution. There are very few models, but these kinds of things are more general. Okay, good. So, let me see. Let's first do the low temperature, or let me see which one is easier. Okay, let's first do the low temperature. So, I will follow the notation of Kogut, and if you read his paper, he's very clear about it. Okay, I'll also try to be clear, but yeah. And it's a very beautiful, exercise. So the first time I learnt about this paper and I understood this thing was also when I was in college in 3rd year. So one of my seniors told me about this paper, and I mean, it was just amazing to learn this. I of course didn't understand the implications very well at that time, but yeah. Okay. Okay, so we have the usual Ising model. Now let me put J to be 1 just for convenience. Okay. So let's put J to be 1. So now when we do the low temperature expansion, so our model is just this, SI/SJ. So when I do the low temperature expansion, I'll do some shifting of my energy just for convenience. It'll make my life simpler. So basically see, suppose you consider a bond here. In this original formulation, the energy of a bond, if it's 2 spins up or 2 spins down, is because J is 1, it's -1, right? That's the energy. And for a bond which doesn't satisfy this constraint, so let's say 1 spin up and 1 spin is down, then the energy is +1, right? This is the energy. All I would do now is to just shift my energy so that this guy is at 0, that's all, and the other guy is at 2. So that's the first shift I'll do. But when I write the final answer, I'll just go back to, yeah. So the way I do this shift is, basically I'll define, so this is the Kronecker delta, okay, this is the Kronecker delta. I'll define an energy thing like this, right? But you see, this is really the same energy as before, because now your ground state has energy 0 and the first excited state has energy 2, right? So this is just a shift in energy, so I'm allowed to do that. Good. So with this, there will be some prefactor hanging around, but we can take care of that. So now again, let's start with the ground state. So let's say I have my big square lattice. Let's say it's really infinite. Okay, let's say it's really infinite, and there are sort of n spins here. So in my partition function, let's say I start with a state. Let's say all spins up. In my partition function, then what is the contribution of this guy? By my new normalization, the energy of this guy is 0. So in my partition function, its contribution is 1, right? Because e to the minus beta times 0, so the contribution is 1, correct? Good. Now we try to create excitations, right? This is my ground state. What is the simplest way you will create an excitation? What is the most simple way you will create an excitation? Correct. Flip 1 spin. So let's flip 1 spin. Now I should use colors. So let's say I flip this spin, right? And every other spin is up, by the way, right? Because I'm just perturbing this, I want to set up a perturbation. So then only these bonds are broken. Right? Each bond breaking gives me a factor of 2. So there is 2 plus 2 plus 2 plus 2, right? So there is 8. So there is an exponential factor e to the minus 8 beta due to the energy cost. Agreed? Everybody agrees? And you should then tell me how many such spin flips can I do, or what is the degeneracy factor associated here? What is that? N square. Careful. Careful. N. That's the answer. So this is a thermodynamically large system. I can do this action on any site, right? I can do this action here. I would get a different state if you wish, right? I can do this action here, do this action here, anywhere. So there are really n ways of doing that, right? Good. So the contribution of this guy is n times this. Good. Now what is the next possible excitation you can think of? 2 spins. Correct. Now we have to be a bit careful. So suppose I think of 2 spin excitations. Naively, you would say that I have broken 8 bonds. Naively, you would say that I have broken 8 bonds. But is that true? Those 2 spins can be anywhere. So first I have to think of the processes which cost me lower energy, because you see the temperature is really high. Oh, sorry, low here. Beta is really high. So I'm setting an expansion in beta. So I should take the low energy processes first and then progressively go to higher and higher energy processes, right? So I need to first take into account processes. Think graphically now. I need to first take into account processes which have the minimum number of wavy lines. So the least number of wavy lines is of course 0. That's the ground state. That gives you 1. The second one is 4. There's no way I can draw less than 4 lines. So this is the contribution of that. Now the third one is actually 6. Somebody I think said 6. So let's draw that, and then you please tell me the degeneracy of that. So let me first draw that. So then the 2 spins which are to be flipped. So now I'm not flipping them. Okay, you understand what I mean when I draw these two. These 2 spins have to be neighbors of each other, right? And then of course there is no wavy line here, right? Why? Because this is a downspin, but this is also a downspin. So I won't draw a wavy line here because this is still a ferromagnetic bond, right? But I'll draw a wavy line here, I'll draw it here, I'll draw it here, here, here and here. Does everybody agree? Is this okay with everybody? Good. So then basically 1, 2, 3, 4, 5, 6. So the exponential factor is what? I have broken 6 bonds. 12. Yeah, 12. Yeah, yeah. Minus 12 beta. Correct? And what is the prefactor? Careful. Oh my God, that's a huge number. Not n into n minus 1. No, no, it cannot be. I'll tell you the reason. See, you don't want the points to go far apart because then you will break 8 bonds, right? You want to just break 6 bonds. So now what is the factor? Just think for a minute. Somebody is saying 4, somebody is saying 2, somebody is saying 1. I in fact even heard a 1 by 2. Of course the prefactor is n. See, this is like a simple counting exercise, right? No, 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 don't do it like this. If you do it like this, you will take your lifetime to count. See, okay, let me tell you the logic. I mean, it's not very difficult, right? It's 2n. The answer is 2n. How do you think of these things? See, you have to draw neighboring spins like that, right? Without repeating structures. So then let's say this is my first spin, which is my seed, if you wish. Then I can draw a horizontal like this, or I can draw vertical like this. You would ask me, oh, why am I not counting this guy? I'm not counting this guy because anyway I've taken this guy into account, and then this structure is automatically taken care of when I take this spin. So I don't want to overcount. So see, I can draw this and I can draw this. Then if I draw this, then obviously the wavy lines are like this. If I draw that, then the wavy lines are like that. right? And so I can do it for each site. So then the number of possibilities is 2 times n, right? Okay. 2 times n. So this thing is 2 times n times e to the minus 12 beta. Good? Okay. Now, let's see. Now, do you think that there is some other possibility? So see, this is 6 bonds breaking, this is 8 bonds breaking. Is there some other possibility? Maybe not, maybe yes, but just tell me. No, there is nothing through which you can break 7 bonds, in fact. You can show that. But then comes the interesting fact. This is the last thing I would do to get the next leading order term, and then we'll put dot dot dot, right? And heroic people have calculated it to very high order. But for our proof, we would see that there's a very nice geometric structure, and you will see it. You will immediately see that there's a 1-to-1 mapping. You don't even need to push it to that order. Good. Okay, so let's calculate processes which have 8 bonds broken. Now, if you naively think about them, you would think that, oh, these processes must scale like n square or something like that. But then actually you will get the counting wrong if you do it like that. So there are actually some sub processes which scale linearly in n. Okay, so you don't, sorry? So, what? Yeah, for example, or even 4 spins on a square, for example. So think about it, just draw a square, flip 4 spins. Yeah, so there are possibilities, right? So yeah, so let me just draw it for you. You can go back and try to think whether there are any other possibilities that I have missed, right? I mean, of course, I understand that everybody has had a nice lunch, so I mean, counting these things gets difficult beyond a point. But so I'll do it for you, because in the morning I was doing it, so so I'll do it for you. In fact, that's interesting. In Kogut's article, there is a small typo, or maybe I don't know, there's an error. There is an error of some prefactors. But anyway, whatever I'm writing, I think all the factors are correct here. Okay, so let me keep these here. And let me also, yeah, so let's just write the degeneracies here. This process contributes n to the power e times 8b. Then there is, of course, another trivial process where there is nothing, that contributes 1. Then this process contributes 2n times e to the minus 12 beta. Okay. So now let me just classify the different processes for you, which comes at when you break 8 bonds. That's the slightly tricky part. These things were easy. That is the one which is slightly tricky, but not too tricky. So let's see. Okay. So there'll be 3 kinds of processes which I'll call A, B, C. Okay. So the first 2, A and B, the key motif is the square. But there's a key difference. The difference is that, okay, I should have used a different color. Maybe, yeah. The difference is that in one case, the first case, case A, I'll flip 3 spins. So see, these big dots mean I'm flipping these spins, right? So now you can see where the wavy lines are. There's one wavy line here. There's one wavy line here. There's no wavy line here, right? There's one here, there's one here, one here, then there is one here, and one here, right? Good. So there are 8. So of course the prefactor is e to the minus 16 beta, right? Now, what is the prefactor in n? This is linear in n, but I need to also calculate the number, right? So I'll just tell you the number, not to torture you. It's actually 6 times n. So I'll also give you the counting because it's very easy to get these countings wrong. But you should do them yourself. Well, I'm giving it anyway. So okay, let's mark a seed site again. So I'll draw some structures and you will see that if you draw any more, you will be overcounting. If you draw any less, you will be undercounting. Okay. So 1, 2. See, you can understand what this means. This means that you flip this pin, you also flip this and this, right? This is what this structure means. Similarly, this. That's all it means. Okay. Then this, yep. Then this, yeah. Then horizontal and vertical. That's it. These are the 6 structures, and that is what you get. Good. So far, so good. So you can try to draw all these 6 structures, and you'll see that they'll give different different configurations. Now, comes B. B is, as you said, on the square. So now, of course, this is also on the square, but here I chose 3 spins to flip. Now I'll choose 4 spins to flip. So of course the degeneracy would be different. So these are the 4 spins, let's say, which I flip, right? Then of course, these are the bonds, which are the wavy bonds, right? So again, the factor is, and please tell me the prefactor here. This is easy. So now I can torture you. Correct. Good. And then the last one, which is the one which gives an n square contribution, is which I'll draw now. So this is the last one here. So basically, you flip a spin here and you flip another spin anywhere else. So then 1, 2, 3, 4, 1, 2, 3, 4. So again, e to the minus 16 beta. But the prefactor here is n times n minus 5. Okay, why is it n minus 5? Okay, you choose the first guy, right? Then you have to choose the second guy. But the second guy cannot be this guy or that guy or that guy or that guy or that guy. If you choose any of these, you will go back to one of those cases that we have done. So then for the next guy, there are only n minus 5 possibilities. So it's n times n minus 5. Good? Because see, 5 because 1, 2, 3, 4, 5. That's why 5. Okay, good. Okay. Oh. Okay, so basically let me just write down the answer here. You see, I also told you that there were some shiftings of energy I had done, so there will be some prefactors which I'll just write now. So if you just go through this, you will figure out those prefactors are correct. Yes? No, no by 2. It's just this. No, no, no. Let's see. Let me just see. So what I'm saying is I mark this guy, right? And then I really remove these points and I draw something here, right? Yeah, you're right. So maybe there's a by 2. Yes. So let's put a by 2. Yeah, so you can see that it's very easy to make a mistake. Yeah. So I cannot blame Kogut. So right. Okay. Good. So right. So okay, so then we write the full answer. So it's beta e to the minus, so this is the factor due to this energy shift which I am introducing now. So it's 1 plus n times e to the, so you see now we have developed, oh sorry, 8, why am I writing 2? So now we have developed a series expansion. Now I'll quickly introduce a way of doing the high temperature expansion, and you will see that there is a one-to-one mapping between all the terms. Good. So of course you can go to higher order. In fact, people have, for this particular problem, gone to an incredibly large number of orders. So last I checked, so that's a bit dated, my information. So maybe people have gone to even bigger order. People could go to this order. Of course, they use some enumeration techniques on the computer. I mean, look, of course, if I count it by hand, it's very easy to make mistakes in such countings, as you can see. I mean, even at this order or at this order, you know, if you're not really careful, you can make factors of 2, factors of n even, right? Lots of mistakes. So it's better to write enumeration codes for these kind of things, and that also requires clever programming. It's a nice thing to do. I have never sat down and done it, but yeah, I would at some point want to do it just to see if I can write a code like this without making a mistake. Okay, so but this is nice. Okay, now we go to the low temperature expansion. So the only thing I would do is to draw those two diagrams on this side, and then I'll erase because I need those two diagrams here. So this is ABC. Okay, let me just draw those two diagrams here. Of course, the identity diagram is trivial, so we won't draw that. So this is this, and the next one is when there is one shared bond. Okay, I did a horizontal. Okay, so let's just do that. Okay. So we have all the diagrams here, right? Whatever we used here. Now I'll erase everything there and go to the high temperature expansion. So in the high temperature expansion, of course, naturally we'll assume that temperature is high, therefore beta is small. So beta will be our expansion parameter, right? So we'll have to search for an expansion in beta. Okay, so I'll erase this. Good. So now I'll do some bit of jugglery and then it'll be immediately clear what I'm trying to do. So now we have a sum where of course we are doing all these traces, and then because j is 1, I really have this guy, right? Good. So now there is a nice property which is easy to verify. If you have any variable sigma which can take value plus or minus 1, if you have any variable sigma which can only take value plus or minus 1, then you can write this equality. And you can just verify it by inspection. Okay, good. So that's point number 1. So let's use that here. So then it becomes cosh hyperbolic beta plus sigma I sigma j sine hyperbolic beta, right? So far so good. Now I'll pull out a factor of cosh hyperbolic beta and soon you will see what's going to happen. So there are, okay, if there are n sides, then there are 2 times n bonds in the system, right? So then I'll pull out this factor because there are that many products here, right? Okay. Okay, good. So now we are almost there. Only other thing I notice that, which is a very obvious thing, but if I try to trace this object, I'll get 0, obviously. Whereas if I try to trace this object, I'll get 2. Okay, good. So now what is the small parameter in this guy? The small parameter is tan hyperbolic beta. Why? Because beta is a small number, therefore tan hyperbolic beta is also a small number, right? So this is my small parameter. So of course I have to arrange my expansion in powers of tan hyperbolic beta. Now again, let's think of a graphical way. So what is this term telling you? It's telling you that, you know, there are many terms like this, like 1 plus sigma 1 sigma 2 tan hyperbolic beta, right? 1 plus sigma 2 sigma 3 tan hyperbolic beta. It's a giant product, right? And so on and so forth. Now suppose you expand this product out, right? Then there will be one term which will have all ones, right? There will be some term which will have all ones but only one tan hyperbolic beta, and so on and so forth, right? So now I adopt a graphical representation where on my lattice, if I draw a dark line, that means that on that line I am considering this guy, and on the other non-dark lines I am considering 1. That's the particular term of the product that I am considering, right? Good. Now, of course, the first thing, the lowest order thing is obvious. I don't draw any dark line anywhere. That's obvious. So that is of course the lowest power of tan hyperbolic beta I can go to. Now let's go to the second thing. Of course, my naive guess would be to draw one dark line, right? That's the simplest thing you can draw. Now suppose you draw this one dark line, then what kind of a structure you have? Let's say you pick up sigma 1 sigma 2 and tan hyperbolic beta. Then really you're left with something like this, and you're doing a trace over sigma 1 and you're doing a trace over sigma 2. What is that going to give you? That's going to give you 0 because of this property, right? Oh, I'm very sorry about my notation. So I think I changed it midway here. So yeah, sorry. But you understand what I'm saying, right? Yeah, good. So you see, of course this will be 0, right? Suppose I draw something like this. Again this will be 0. Why? Because let's say this is S1, this is S2, this is S2 and S3, then it's like there's a term S1, S2, then there is a term S2, S3. S2 times S2 is 1, which is fine, but there is still this S1 and S3 hanging around. I cannot do this, again the trace is 0, right? So the only kind of diagrams I'm allowed are closed loops. The loops have to close, they cannot have free ends. That's it, right? Because if they have free ends, if I do the trace, because of this property, those diagrams will just give 0. Good. So what is the first diagram here? This guy, right? This guy. So then let's see. So then what is the energy factor here? Yeah, the energy, so one thing. Yeah, again there are some normalizations here which I'll write at the end, okay. So let's say the most basic diagram, which is this, nothing here, contributes 1, okay. Then this guy, how many factors of tan hyperbolic beta does it contribute? Sorry, somebody said the right thing. Yeah, 4. A bit louder. If you speak so softly, nobody will be able to hear you, right? So this thing, what is the degeneracy? N, right. Now see a very nice correspondence. Let me use some other color, pink. Look at this. Let me take the dual lattice of the square lattice, right? So what is a dual lattice? I just take this lattice and mark the center points, right? Mark the center points. This is called the dual lattice. Wherever I see a dark line on my original lattice, I draw a wavy line which cuts the dark line, right? So then I draw a wavy line here, I draw a wavy line here, I draw a wavy line here, I draw a wavy line here. But that's exactly this diagram. That's exactly this diagram. So instead of drawing there, let me now come back and draw everything here. That's it, right? So now you see what's going to happen. So the lowest order process is this. And the counting is exactly this. Whatever is the counting I got there has to be the counting that I get here, right? Then the next order process is this, 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 this. I cannot draw a line here because then this guy would have an odd number of terms, and that is not allowed because SI cube is also SI, and then it will vanish by trace. So this is the next significant term, right? Let's come here. This. You see, I'm just drawing all the diagrams straight away. This, and the counting is again the same. That's it. You can convince yourself that these are all the closed loops you can draw. Just sit with a piece of paper and some free time. Well, you don't need much time. In fact, yeah, you can already see what's happening, right? So I have hopefully shown you that term by term, you can identify term by term the contributions of this series at high temperature with the contributions of this series at low temperature, right? It's a one-to-one correspondence. Okay, good. So now I'll just use that, and I have shot a bit above, but I really want to finish this. So maybe I'll take a few more minutes, and it's almost towards the end because this is the main point, right? Okay, so then I suppress some normalizations. So let me just write those normalizations for you. So at low temperature, the expansion that you will get is the following. So this is clear because this factor goes on that side. There's another factor 2 to the minus n. Why is it there? Because you see, when you have closed loops, everything becomes 1, and then you keep tracing it. So you get a 2 each time, and there are n spins, so you get 2 to the power n, and you just pull it on this side. Plus dot dot dot. Let me not write the other terms. You can immediately write the other terms, right? Just by looking at this guy. Now notice a very nice correspondence. Let's look at this series. Let's look at this series. I want to do something so that this series starts looking like that series, right? At least look at the right hand side. I want to do something so that the right hand side of this series starts looking like the right hand side of that series. But that's very easy to identify. Just do this. Tan beta now just check whether you can identify this thing with that thing, right? Okay, so yeah, then basically what you can see immediately is, okay, let's see, this is an equation which relates some beta to some other beta, right? Now, let's say this beta is large. What do you think this beta would be? Suppose this beta is large, right? If this beta is large, then this is like close to 1. Then what is this? No, I'm saying it the other way around. Exactly. Yeah, so you should have caught me there. Yes. If this is large, this is a huge exponential, but with a negative here, it's close to 0. And then tan hyperbolic beta, when it's close to 1, automatically means that beta is very large, right? Because it asymptotically goes to 1. So you see, if this beta star is small, beta is large, and vice versa, right? So this is a very interesting mapping which does the following. Maps the low temperature side of the Ising model, 2D Ising model, to the high temperature side. So you can find a temperature here, and by doing this transformation, if you know the physics here, you can actually with this transformation try to calculate the physics here, and vice versa. So this is a very interesting duality because it connects the low temperature side to the high temperature side, and vice versa. Then what is the fixed point in this language, or what is the critical point in this language? See, there is something called low temperature and there is something called high temperature, or another way of looking at it is there is something called broken symmetry phase and unbroken symmetry phase, right? So this transformation takes you from here to here, and so on and so forth. So then the only place where basically this thing can give the same number is if you're exactly at the critical point, right? Because otherwise it'll take you from broken to unbroken or from unbroken to broken. So the only place where this guy can give again the same point is at the critical point, right? So now you know the critical point. You just solve this equation where you say that this is also beta star and this is also beta star. So I need to find that solution, and if you find that solution, so this is not hard. If you find the solution, you'll find that this is 2 times, now I insert a j just for historical reasons. Just by solving that equation. And this is exactly what you got from Onsager's solution, right? Therefore, this is the proof that this is the TC, and TC is finite, it's not 0. So I hope everybody is convinced, right? Good. Yes. Yes, yes. You mean quantum spin? But this is a classical model.
But so the classical model, is it possible to get plus half or minus half?
Yeah, that you can do. That you can do. That will just rescale the coupling of your Hamiltonian. That you can do. That is not a problem.
I mean, whole calculation
Yeah,
remains same.
Yeah, of course. It will remain same. It will remain same. Yes.
Another question.
Yes.
A little bit disconnected.
Mhm.
Still I am asking you.
Oh.
What is the difference between steady state and equilibrium?
Oh, this was already discussed in the previous things. So as other people have discussed, and they know much better than me, but I can still try to answer. So in equilibrium is a more restrictive thing. Steady state is things become independent of time. But equilibrium is even more restrictive than that. There is something called detail balance in equilibrium in phase space. And what it means is that there are no macroscopic currents in the system in equilibrium. Whereas in a steady state, there can be a time-dependent macroscopic current in the system. That's one simple way of. Do you want to add anything? Okay. Oh, see, I told you that. Okay. See, now you have attained this interesting duality, right? Which relates the high temperature to the low temperature, right? Now let me make an assumption. Let me make an assumption that the 2D Ising model has a Z2 broken phase, which you call the ferromagnet, and a Z2 unbroken phase, which you call the paramagnet, right? Good. So what this transformation does is, if I give you a temperature here, then of course solving that equation, now let's remove the star. If I give you a temperature in the low temperature side, you can actually get a corresponding high temperature, and then you can relate both the partition functions. Because you can relate both the partition functions, you can calculate the thermodynamic quantities here just by knowing the information here, right? That's this duality, right? So you can relate a point here to a point here, a point here to a point here, and so on and so forth. Now, so a broken symmetry state goes to an unbroken symmetry state, and vice versa. So what is the condition when this beta goes to the same beta under this equation? The only time it can happen is when you are right at the critical point, right? Because if you are on the broken side, you will go to the unbroken side. Whereas if you are on the unbroken side, you will go to the broken side. So the only place which is sort of the quote unquote fixed point of this equation, which means that you put in a temperature, it gives you the same temperature out. The only place that can happen is at the critical point. And so we just use that property. Of course, there was an assumption there that there is a single critical point, nothing else. So that's an assumption. But let's say I assume that, and then I use this property, then I get the right critical temperature. So it also holds for the anisotropic Ising model. So suppose you make these couplings. Let's say you make this coupling J1 and that coupling J2. That's a slightly harder calculation, but you can still show a duality then. But if you put next nearest neighbor interactions and so on and so forth, then this duality does not hold. See, this duality is a very special property of this class of models. It's a very special property. Yeah, I also think so. Yeah, I don't exactly recall the paper now, but I once read that it does hold for the yeah.
What's proved it?
Yeah, yeah, yeah. Exactly, exactly.
Through a very different.
Yeah, yeah, yeah. Correct, 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 correct. That's true. That's true. For the Ising, it's actually easier to do the calculation. That's why I did. This is very straightforward to understand it. So
What's also one can develop high and low. But
perhaps, but I haven't tried that. It's a good thing to try.
And for JXJY, beta star, beta C is known explicitly.
Yeah, yeah, it's known. It's known. It's known. Yeah, and the duality can also be shown. It's not so easy like this one. It's slightly harder, but it can be shown.
Sir, this is a classical system.
Yes.
So is there any quantum person? I mean,
Yeah.
as I know, I think d-dimensional quantum system is equivalent to d plus y one-dimensional classical.
Yeah, sometimes that is true. There are important exceptions to that rule. But coming back to this model, which is the 2D Ising model, has an interesting quantum partner, if you wish, which is the 1D transverse field Ising model, and that also has a duality, which is similar to this duality. But I don't want to go into too much details. I'll just write down the model for you, and then you can read up on your own, because there are several articles and books on this quantum model as well. So the quantum model is just this. So let's say you have spin half degrees of freedom on a line. Okay, so this is a line. You have spin half degrees of freedom. So let's write a Hamiltonian. So the first term is like an Ising term, but there is another term here, which is like this, right? So there is a SIX here. So this model is called the transverse field Ising model in one dimension, and this also has a duality, and you can connect this. So this is in d equal to 1. You can connect this model to actually this model. Yeah. Yeah, yeah, you can take SIY, but you cannot take this term and that term together. You cannot take both of these together. Then there is a problem. Then this duality breaks down. It's no longer there. Yeah, yeah. Because I did that shift originally, and that's why it came. No, 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 they don't. In fact, I needed to do it, but I just didn't in view of the time. You can do a bit more massaging of the cos hyperbolic, tan hyperbolic, everything, and you can show that there is a z beta equal to z beta star divided by some function of beta and some function of beta star, and those two functions are also the same. Yeah, yeah. But you just have to do some more manipulations. But already the central point should be clear. But yeah, the answer to your question is it can be done, and in fact that's natural to expect, that if the duality holds, then even the denominators are the same in functional sense.
So it seems like for high beta also the two would match. Actually,
No, that cannot happen. You see, this relation, if you put a low beta here, you will automatically get a high beta star here and vice versa. That is the nature of this relation. I mean, that's the nature of this, right? This is the way tan hyperbolic and exponential functions behave. So maybe you're making some algebra mistake, but we discussed this in the last lecture. This is just the total magnetization of the system. Okay, good.